Dear students, in the last session we have derived the Navier Stokes equation in a more generic form for both compressible as well as for the incompressible form. Let me recall the equation what we have derived in the last session. Rho into du by dt is equal to dou by dou x of sigma xx plus dou by dou y of tau xy plus dou by dou z of tau xz plus rho into fx. This equation is called as the x momentum equation or the momentum equation along the x direction. Similarly, this rho into d small v by dt is equal to dou by dou x of tau xy plus dou by dou y of sigma yy plus dou by dou z of tau yz plus rho into Fy. Similarly, if we want to write for the z momentum equation, it is rho into dou w by dou t will be equal to dou by dou x of tau xz plus dou by dou y of tau yz plus dou by dou z of sigma zz plus rho into fz. So these three equations are known as the general Navier Stokes momentum equation for a real fluid. For a real fluid means a fluid which possesses viscosity. A fluid which has viscosity. For that particular fluid, the corresponding conservation of momentum equation is known as Navier Stokes equation. On the other hand, if this equation for the conservation of momentum is derived based for a ideal fluid in which there is no viscosity or if the viscosity effects are not considered, then that particular type of momentum equation what will be deriving will be reduced to Euler's equation. It's called as what? Euler's equation. So these equations are nothing but what? The momentum equation which we have derived in the last session. Now in this section, this equation is common for both compressible flow as well as incompressible flow. In this session, let us try to develop the Navier Stokes equation for an incompressible fluid. So our approach is for now for an incompressible fluid. Let us try to find the equation. So what we are going to do means we are going to substitute the value of sigma xx, tau xy, tau xz and sigma yy, sigma zz as well as the other shear stress term and normal stress term in this equation, and we are going to find the solution. And right now I am not going to disturb the left hand side. And right now we are not going to disturb the left hand side. We are going to just work on the left hand side. Let us see how this equation will become. Okay, I will take only the x momentum equation for understanding. And we are going to work mostly on the RHS. We are not going to disturb the LHS. We are going to work on the RHS. Okay, we know that sigma x is equal to what? Minus P plus 2 mu into dou u by dou x minus 2 by 3 mu into del dot B. So this one we know for sigma xx. As well as I told tau xy, how we had write? We had write as mu. Then we had write as dou by dou x plus dou by dou y. Wherever x is there, or here y is there, so I had to put v here. Here x is there, so I had to put as what? U. So it will be the normal component. For x, the normal component is v. For y, the normal component is u. Okay, similarly, if I want to write tau xz, how to write? Mu of, first we have to write x and z. So it is dou by dou x plus dou by dou z. Since here z is there, I will put here as w. Since x is here, I will put as u. I will put as what? U. Similarly, if you want to write tau, these terms are fine. So we will try to substitute the value of sigma xx, tau xy and tau xz in the RHS of this equation. So the equation will become dou by dou x of minus P plus 2 mu into dou u by dou x minus 2 by 3 mu of del dot V plus dou by dou y of tau xy, which is nothing but mu of dou by dou x plus dou by dou y of v of u here plus dou by dou z of tau xz. Tau xz is nothing but mu of dou by dou x plus dou by dou z. So it will become now w, here will become u plus rho into fx. So the left hand side is what? Rho into du by dt. That's what I told. I am not going to disturb on the left hand side. We are going to work only on the right hand side. So this one. Now we are deriving the Navier Stokes equation for the incompressible fluid. So right now let us work on only the RHS. Okay, the left hand side we will see it later on. The left hand side we know is what? Rho into du by dt. Let it be LHS. So now we are going to work only on the RHS and finally we will equate them. So it will become what? Minus dou p by dou x plus 2 mu into, you can see, I am going to multiply dou by dou x of 2 mu into dou by dou x. So 2 mu of dou squared u by dou x squared. And we know for an incompressible fluid, the continuity equation is what? Del dot v equal to 0. I will repeat once again. For an incompressible fluid, continuity equation is del dot v equal to 0. What is del dot v equal to 0? Dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. So this term becomes 0 because when a Navier Stokes equation or the conservation of momentum equation is satisfied, basically the continuity equation should also be satisfied. The conservation of mass equation should also be satisfied. This is the continuity equation for a incompressible fluid. Now we are discussing about the incompressible fluid, so definitely this term will become 0. So there is no need to write this one because 0 into anything will be 0. So I hope you got the logic. Why this term vanishes? Because of the continuity equation for an incompressible fluid. That's fine. Now we will write here, this is mu into dou squared v by dou x dou y. Simply I multiply dou squared v by dou x dou y or dou y dou x into mu plus mu into dou squared u by dou y squared. Similarly, I am going to write for this term, is a term. So it will become plus dou square w by mu into dou square w by dou x dou z. Okay, I am multiplying this term plus mu into dou square u by dou z squared plus rho into fx. So after simplification, just I have substituted the values of sigma xx, tau xy and tau xz in the x momentum equation, and I made delta v equal to 0 because that is the corresponding continuity equation for the incompressible fluid. The final expression has been obtained. On proceeding further, I can write this is what? It is like this term within the bracket, this term is called as x. Mu into dou square u by dou x squared is there. So it is 2x. So I can write as x plus x. So what I am about to tell here is nothing but minus dou p by dou x plus mu into dou squared u by dou x squared plus mu into dou squared u by dou x squared. If I am going to add, what will happen? 1 mu into dou squared u by dou x squared plus 1 mu into dou squared u by dou squared will become what? 2 mu into dou squared u by dou squared. I have written 2 as 1 plus 1. That's it. I have written 2 as what? 1 plus 1. Plus, I will write now this term plus mu into dou squared u by dou y squared. So this term is over. This term is over. I have written this term also. I am going to write now this term also. So plus mu into dou squared u by dou z squared. Okay. Okay, fine. Now what are the other terms left out? Plus this term is left out. So we can write this term. Plus mu into dou squared v by dou x dou y. Then which term is left out? This term is left out. Plus mu into dou square w by dou x dou z. Plus the last term is the body force term. Plus rho into fx. I hope you got it. What I did in this equation, I simply made this 2 as 1 plus 1. Then I written the term dou square u by dou y squared plus mu into dou square u by dou x squared. All this term combinedly. Why I written combinedly like this? Out of these 3 terms, I can take mu as common. So it will become what? Dou square u by dou x squared plus dou square u by dou y squared plus dou square u by dou x squared. That is the logic. we have rearranged the terms. We have rearranged the terms. So let us proceed further. It's only mathematical work. There's no much physics here. So it will become minus dou p by dou x. Now I'll give importance to the term within this bracket. So it will become what? Mu of dou squared u by dou squared plus dou squared u by dou y squared plus dou squared u by dou z squared. Plus one more this term is there. Now we have completed term within this bracket. I have taken mu as a common term. Plus mu of, I am going to take out of this term dou by dou x as common term. From which one? From this term, I have taken only what? Mu into dou by dou x as the common term. So whatever the remaining term, it will be dou u by dou x. Now you multiply and see what is happening. Mu of dou squared u by dou squared. This term is obtained here. That term is obtained here. Plus I will take this term. I will take mu into dou by dou x as a common term. The remaining term will be what? Dou v by dou y. Otherwise you multiply and see what is happening. Mu into dou squared v by dou x dou y. So mu into dou squared v by dou x dou y. So we will get this term if we are going to take this one. Plus in this term I am going to take what? Mu into dou by dou x as common term. The remaining term will be what? Dou w by dou z. So it will be dou w by dou z. Plus, don't forget to write the body force term, plus rho into fx. Now, can you tell what is this value? It is what? Dou u by dou x plus dou v by dou y plus dou w by dou z. So what is the value? Yes, you are right. This value will be equal to 0. Why? Because it's nothing but del dot v. Del dot v equal to 0 for the incompressible fluid. That is nothing but the continuity equation for the incompressible fluid. So this term vanishes once again. Y means this term is nothing but what? Del dot v. But we know for incompressible fluid, del dot v equal to what? 0. So this term vanishes. What about this term? This term is nothing but what? Second order derivative of u. So it is nothing but called as what? Del squared u. So I can write as minus dou p by dou x plus mu of del squared. What here del squared indicate? Del squared indicates I of dou squared by dou squared plus j of dou squared by dou y squared plus k of dou squared by dou z squared. So I can write this entire term as what? Del squared of u. Del squared of what? U. Okay, fine. Plus this term vanishes. Plus rho into fx. What about the left hand side? The left hand side I will take it from here. Is nothing but rho into du by dt. So we got the x momentum equation for the incompressible fluid. This is the x momentum equation for the incompressible fluid. Similarly, if you are going to derive, then I will end up with what? Rho into small dv by dt will be equal to minus dou p by dou y plus mu into del squared small b plus rho into Fy. This equation is called as what? Y momentum equation for an incompressible fluid. Then I can write it for what? Rho into dw by dt is equal to minus dou p by dou z plus mu into del squared of w plus rho into fz. So now this equation gives me the z momentum equation for an incompressible fluid. So now let us say the equation number 1, 2, 3 indicates the x momentum, y momentum and z momentum equation for an incompressible fluid. Let us proceed further to derive the other forms of the Navier Stokes equation for both compressible as well as incompressible by changing the what? The LHS. So we will proceed further. And dear students, in the previous session we had derived the momentum equation of x, y and z for a general fluid, whether it's compressible or incompressible, by equation number 4, 5, 6. In this session, just now we have derived the what? The x momentum, y momentum and z momentum for an incompressible fluid represented by the equation 1, 2 and 3. Now you can see whether it is compressible are generic and this is incompressible, the left hand side still remains the same. So there's no change in the left hand side. Only we can see the form has modified in the right hand side when you are coming for the incompressible fluid, when you are substituting the values for sigma xx, tau xy and tau z. Finally the expression reduced to 1, 2, 3 from 4, 5, 6. From 4, 5, 6. In some books they may given like this. Sigma xx is nothing but is equal to minus p plus tau xx. Okay. Otherwise they also may given like this. Sigma yy is equal to minus p plus tau yy. Similarly sigma z is equal to minus p plus tau z. Okay. So instead of sigma xx, some book may given in the form of tau xx and p. So I can replace now the sigma xx what? Minus p plus tau into yy. So it will become minus, so I will write here minus p plus tau xx. Can I write like this? Because sigma x is equal to minus p plus tau xx. Where tau xx will be equal to 2 mu into dou u by dou x minus 2 by 3 mu of del dot b. Already we have seen what is the value of sigma xx. So other than minus p, what are the terms which are there? You may take it as what? Tau xx. Okay, so I have taken the sigma xx as what? Minus p plus tau xx. When I am going to differentiate both this p and tau xx with respect to dou by dou x, this term will become two terms. One is minus dou p by dou x and the other term will be what? Dou by dou x of tau xx. So I left some space. So I can write now like this. So instead of this term, I can write as what? Minus dou p by dou x plus dou by dou x of tau xx. So either you can write as dou by dou x of sigma xx, or in some books they may refer as what? Minus dou p by dou x plus dou by dou x of tau xx. Similarly, now I can change this sigma y as what? Minus p plus tau yy. So this term can be written as what? Minus dou p by dou y plus dou by dou y of tau yy. Similarly, this sigma xx can be replaced as what? Minus p plus tau z. So this term will become what? Minus dou p by, this term is dou z, not dou x. So dou z plus dou by dou z of tau z. So this also a form where you can represent sigma xx as what? Minus p plus tau xx, because we want mostly the pressure gradient term. Minus dou p by dou x, minus dou p by dou y, minus dou p by dou z. In order to we want to have a separate term with respect to pressure, we can also write the sigma xx like this. So in some book we also prefer this one. So once again, the equation 4, 5 and 6 are nothing but the momentum equation for a generic fluid. Either it can be compressible or incompressible. Whereas the equation 4, 5 and 6 will become like 1, 2, 3 when it's going to be incompressible. When it's going to be incompressible. Now the beauty is that whether it's going to be generic or incompressible, the left hand side still remains same. Now we are going to work in different way such that this left hand side will get changed. The left hand side will get changed. So now we are not going to disturb the RHS. Now we are going to work on only on the LHS. I am going to work on rho into dou by dt. Whether it's for generic or for incompressible. I am going to work for only rho into dv by dt. Similarly, I am going to work on rho into dw by dt. Okay. Dear students, let us now continue with the LHS of the momentum equation. Now let me take the x momentum equation, and the corresponding term on the LHS is nothing but rho into du by dt. Here I want to tell what is du by dt. In the earlier session in our video, we have explained more about the substantial derivative. The substantial derivative, if it is going to be dt by dt, it will be equal to what? Dou t by dou t plus v dot del of t. Please refer my earlier video on substantial derivative. You will come to know how we write this one. So here instead of the variable t, we have the variable as what? U. So we have du by dt. So du by dt will be equal to dou u by dou t plus v dot del of, here what is the variable? Here the variable is u. So you write like this. So now instead of du by dt, I can substitute this value here. Okay, substitute now 7 in this equation. Namely, we can call this equation as 8. So substitute what? 7 in 8. Only for the rho into du by dt. So what is du by dt? Du by dt is nothing but dou u by dou t plus v. This v is the velocity velocity dot del of u. Okay, so based on the substantial derivative, we are expecting the term for du by dt as dou u by dou t plus v dot del of u. Please refer my earlier video on this particular substantial derivative. Okay, now let us, this term become like this. So it become now rho into du by dt plus rho v into del of u. Del of u. So this is the LHS now we have. Earlier my LHS was like this. Now this has been transformed into what? Rho into du by dt plus rho v into del of u. I hope you can get it. Now we want to substitute the value for these two terms so that we can complete the LHS. Okay. Now let us take a term like this. What will be dou by dou t of, I am sorry, this will be small, this one we have to replace as what? Dou u by dou t. Okay, rho into dou u by dou t plus rho v into delta u. So now we can see, I am going to find dou by dou t of rho u. Can anyone tell what the value of this differentiation? Now we have two variables, rho and u, because it can be for both compressible or incompressible. So rho is a variable also. So we have two terms. So we have to go for uv rule. U dv plus v du. So it will become rho into dou u by dou t plus u into dou rho by dou t. This is fine. So if I want to differentiate dou by dou t of rho u, it will be equal to rho into dou u by dou t plus u into dou rho by dou t. Out of which I want only this term. Let us call this equation as equation number 9. In this term I want only what? Rho into dou u by dou t. So I want only this term. So from 10, you try to get a value of rho into dou u by dou t. What is the value? Dou by dou t of rho u minus u into dou rho by dou t. So otherwise I will write one more step. Rho into dou u by dou t will be equal to dou by dou t of rho u minus u into dou rho by dou t. So now you substitute the value of 10 in this equation number 9. So I will be substituting right now because of space constraint. I will write now itself. So now rho into dou u by dou t can be replaced with this term. So it is dou by dou t of rho u minus u into dou rho by dou t plus this term. This term is nothing but rho v into del of u. So still we are working on the equation number 9 only. Let us explore further. This is the modified form of the LHS. So it's dou by dou t of rho u minus u into dou rho by dou t plus rho v into del dot u. So now I am going to change this term also. How will let us see? Now let us take this one. Del dot of rho u v. In this one, I will take rho v as a single variable and u as another variable. So it can be written as what? Rho v into del of u plus u into del of rho v. Got it? How I am taking? So I will repeat once again. I am going to simply find del of rho u v. Why I am finding, I will tell you later. So del of rho u v I am going to find out. So out of these three variables, I am going to couple rho and v. So rho v I am taking a single variable into del of u plus now I am going to take u outside and make rho v as the differential. So u of del of rho v. So from this what I want, you see, this term only I want. Why? To substitute over here. To substitute over here. So what about this term will become now del dot rho u v minus u dot del of rho v will be equal to what? Rho v into del of u. Okay, so we got this expression. So we can substitute for rho v dot del of u as what? These two terms. So I will replace directly. I hope you are able to understand. I will repeat once again. I want to replace this term with also with some other term. Which term I have taken for that? I have taken del of rho u v as a operator. Then I am trying to make rho v as a single term. So rho v of del of u plus u into del of rho v. From this I want only this term. So keep this term on the left hand side and take this term to the other side. So I got this expression. Now substitute for this term from here. So now what will happen? This term will become del dot rho u v minus u dot del of rho v. So this is my LHS of the, this is the LHS of what? Now actually what is this value? This value is nothing but rho of du by dt have been transformed as what? Like this. Have been transformed as like this. Okay. One more step only. Now I will tell you. I will take the first term. So dou by dou t of rho u. I will take the third term also. Plus del of rho uv. In these two terms, I am going to take minus u as common term. In these two terms, I am going to take minus u as common term. It will become what? Dou rho by dou t plus del of rho v. So got the logic? I have written the first term first, the third term as the second term here, and I combine the second term and the fourth term by taking minus u as the common term. So it becomes dou rho by dou t plus del of what? Rho v. Can anyone tell what is the value of this term? What is this actually? This is nothing but what? Continuity equation for any fluid. It is for any generic fluid, whether it's compressible or incompressible. Okay, so what is the formula? We know the equation is what? Dou rho by dou t. What is del? Dou by dou x plus dou by dou y plus dou by dou z. What is rho? Rho is rho everywhere. What is v? U, v, w. And we know this continuity equation will be equal to what? 0. Because this is the continuity equation for any generic fluid, which means this term will become 0. This term will become 0 because this is the continuity equation value is equal to 0. We know already. So now my LHS become dou by dou t of rho u plus del dot rho uv. So what I am telling means the LHS rho into du by dt becomes dou by dou t of rho u plus del dot rho uv. Still it can be further expanded like this. Dou by dou t of rho u plus instead of del we can write as what? Dou by dou x plus dou by dou y plus dou by dou z. I can't change rho. Rho is rho everywhere. I can't change u. U is everywhere u. But we can write as what? U, v, w. So rho u into u will become u squared. So now the expression the left hand side becomes like this. Instead of writing as rho into du by dt, I can write as what? Dou rho by dou t plus dou by dou t of rho u plus dou by dou x of rho u squared plus dou by dou y of rho uv plus dou by dou z of rho uv, rho u w will be equal to the corresponding RHS. Will be equal to the corresponding RHS. So now we have established that the LHS as rho into du by dt as what? Dou by dou t of rho u plus dou by dou x of rho u squared plus dou by dou y of rho uv plus dou by dou z of rho uv, rho u w. As well as we have seen earlier the u momentum equation for an incompressible fluid as what? Rho into du by dt equal to this term. Now we are going to change only the left hand side. So the left hand side now will become what? Dou by dou t of rho u plus dou by dou x of rho u squared plus dou by dou y of rho u v plus dou by dou z of rho u w is equal to minus dou p by dou x plus mu into del squared u plus rho into fx. So I hope now this equation is also what? The u momentum equation only for the incompressible fluid only. But we have modified the left hand side. Similarly, like what we have written for rho into du by dt, we can also write it for what? Rho into dv by dt, which will be equal to what? It will be equal to dou by dou t of rho v plus dou by dou x of rho uv plus dou by dou y of rho v squared plus dou by dou z of rho vw. Similarly, we can write rho of dw by dt as dou by dou t of rho w plus dou by dou x of rho uw plus dou by dou y of rho vw plus dou by dou z of rho w squared. So now I hope you can replace the terms for rho into du by dt, rho into dv by dt and rho into dw by dt for all the first six equations. 1, 2, 3, 4, 5, 6. We will arrive the final Navier Stokes equation. I hope you may enjoy the session very well and you may understand the terms each and every time very clearly. Thank you.